I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on deriving Bernoulli's principle. Alright, so what I have set up here is I've got a catch basin for some water. Inside the catch basin I have a ruler so I can measure some distance. I also have a ruler taped to a plastic bottle that's filled with water, and that bottle also has a hole that is punctured into the side of it. So what we're going to do is we're going to just make some observations. So go ahead. Yeah, I know, it looks kind of funny, but it is what it is. So go ahead and pause the video, make some observations, and I'll show you some of the observations my students made right now. All right, so we've made some observations, and some of the observations that my students made was, one, the range of the water is going to depend on some variable, and the height of the water in the column of the plastic bottle is going to vary. Obviously, more water comes out, the level is going to drop. So a couple things that we can measure. We can measure the depth. So I have this ruler taped right here so that 0 is right where the hole is. Now this hole happens to be 0.28 meters from the bottom of the catch basin. So we could use the other ruler to measure how far the water has gone. So what we want to do is we want to find a relationship between height of, or the depth of the water. So the depth would be from the top of the water down to the hole, that would be the depth. And we're going to figure out the velocity in which it exits. How are we going to figure out the velocity? Well, here's how we're going to figure out the velocity. We know that the water is a projectile. We know that the height is 0.28 meters. So we can use simple kinematics. We know that once it becomes a projectile, a horizontal launch, the initial velocity is 0 in the y direction. So we can figure out an equation for the time. And then we know that the velocity is constant for a projectile in the horizontal direction. So we can go ahead and just calculate the horizontal velocity simply by doing the horizontal range divided by our equation for time. All right, so we have our setup, and what we want to do is we want to determine the time that it takes to drop this height. So as we learned in kinematics, we're going to list all of our kinematic variables. From this, we're going to define the variables that we know. We know that the final height is a height of 0. We know that the initial y velocity, since the water is launched horizontally, is 0. We know that acceleration is negative g, and we're looking for an equation for time. Since we don't know the vertical velocity final, we're going to go ahead and look at our second kinematic equation listed on the AP formula sheet. Now notice from the AP formula sheet I changed all x's to y's because we're looking in the vertical direction. Now we're going to plug in the values that we know for each of those. We know that the initial y velocity is 0, so that's going to be 0 for vy naught times t. So that leaves us with minus 1/2 gt squared. Now we're going to rearrange this equation and solve for time. We get that t squared is equal to 2y0 over g, and then we take the square root of both sides to get an equation for time. So t is equal to the square root of 2 times the initial height divided by g. So this is how you're going to calculate your time. Once we know the time, we need to find the horizontal velocity. So we look at the horizontal equation. So we're going to use the same kinematic equation, except horizontally, the velocity does not change. So there's no acceleration. So we're only going to need the x is equal to x naught plus vx naught times t. And from that, we can derive an equation to calculate our velocities, which would be the velocity of the water as it leaves the hole of the plastic bottle. So what we're going to do then is we're going to go ahead and record our data in terms of horizontal position and depth, and then we will convert our horizontal positions into velocity by using the time that we calculated for the given height, and then we will make a graph of velocity on the vertical axis and the depth of the water on the horizontal axis. So go ahead and collect your data points. I'll see you in a minute. And now we need to graph it. We go to our graphical method summary sheet and we have this side opening parabola. So we see that v squared is proportional to y. So you should have ended up with an equation after you analyzed your data. V squared equals some slope in parentheses times with unit of meters per second squared, and you should multiply that by y. So v squared is proportional to y. This situation is going to be a little bit tricky to figure out the meaning of the slope. So what we're going to do is we're going to multiply each side by mass. Now this slope is in meters per second squared, which means it's an acceleration. So what we're going to do is we're going to look at an energy bar chart. So in our initial situation, we have all potential energy as the water is moving downward from the top of the bottle, and at the hole that converts it all to kinetic energy. So we have UG is equal to K. Substituting the equations in for each of those, you can see that this looks very similar to what we have in our mathematical model derivation. We've got the mv squared and we've got the my. So now we just need to rearrange these, and we're missing the g and the 1/2. And I multiplied both sides by 2, so we can see we've got the my on one side and the mv squared by itself. So let's rewrite it the way we have it, mv squared on the left side. And what we're missing is the 2 and g. So we're going to use that. That should be the meaning of our slope. So now what we're going to do is we're going to put this, normally we're not going to find the mass of the water. It's more likely we're going to use density. So we're going to use this density equation. And we're going to rearrange this equation for solve for mass. And then we're going to substitute that in for our masses in each situation. We're going to cancel out the volume because the volume is a variable that could change, but the density is a constant. So we're going to use density instead of volume. And we'll divide each side by 2, and we end up with the equation of 1/2 the density of water times v squared is equal to rho gh, which we've seen this rho gh before. Rho gh represents the pressure of the water at a specific depth. So what we've done here is we have this equation, and we can see that the 1/2 rho v squared is equal to rho gh. So we have a variation of conservation of energy. Now that means all of the energy at the beginning is going to equal all types of energy at the end, because you could have situations where that the water is moving instead of being static in the bottle. So we're going to go ahead and look and derive Bernoulli's principal equation, which is on your formula sheet. So you can go ahead and take a look at that to derive. Now, the reason that you would not have exactly 2G is because of something called viscosity. Viscosity is the friction within a fluid. So there's friction, internal friction, that's going to cause the water to not go as far, which means the velocity has a little bit of friction, so it doesn't reach its maximum velocity because of that viscosity. So here is deriving Bernoulli's principle. Have a great day and an even better tomorrow.
If you found this video helpful, don't forget to subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.